Imagine driving at nearly twice the height of the Eiffel Tower, so high you literally pass through clouds. That's the reality on China's Huajiang Bridge, inaugurated in September 2025 and instantly becoming the world's new record holder. The bridge deck sits at 625 meters above the water below. But that wasn't the craziest part. This structure stretches across one of the most treacherous gorges in western China, where harsh terrain and dense fog layers have killed previous projects before construction even started. And on top of one tower, they built a glowing café in the clouds. Something that sounds like pure fiction but is completely real. Welcome to Macro Forge, where we explore engineering that defies every logical limit. If structures that shouldn't exist fascinate you, hit subscribe. What you're about to see will blow your mind. This record-breaking bridge emerged from one of China's most unforgiving regions, Guizhou Province. Over 92% of its territory consists of high mountains and plateaus. Between them flow 8 major rivers plus countless tributaries carving deep valleys that make transportation a nightmare. For decades, communities remained isolated, not by choice, but by geography that refused cooperation. Engineers needed to build the Luji Anlong Expressway, connecting Lupanshui with Anlong County. The route was forced through the dangerous junction of the Beipan River within Huajiang Gorge, and that's where everything got complicated. During survey phases, engineers confronted 2 equally expensive options: build gentler approach roads but place the bridge near mountain peaks, or build the bridge lower, running it across steep slopes requiring long tunnels. They chose the challenge, 625 meters above the river. But that decision created a problem nobody had solved before. The V-shaped gorge created a distance exceeding 1,400 meters between cliff edges. At that scale, every conventional bridge type failed completely. The tallest rigid frame bridge in the world couldn't span it. The longest arch bridge, not even close. The largest cable-stayed bridge, insufficient capacity. Only one option remained, a suspension bridge with an ultra-long main span capable of meeting these extreme requirements. But building it would prove almost impossible. In principle, suspension bridge construction follows 3 steps. Build the 2 towers, pull the main cables into place, and anchor them securely. Hang the bridge deck using suspension cables. Simple theory, brutal reality. The Huajiang Bridge stands 625 meters above the river, spanning 1,420 meters across the canyon. When including tower structures, the total height rivals the tallest buildings ever constructed. With numbers this enormous, construction demands went far beyond standard infrastructure projects. Then they discovered the real problem. The foundation had to be drilled deep into weathered rock layers filled with cracks and groundwater. One miscalculation meant catastrophic failure. Engineers deployed a specialized piling system driving 24 massive concrete piles deep into unstable ground combined with anti-seismic steel reinforcement, ensuring towers could withstand decades of operation. But unstable foundations were just the beginning. What came next would test every engineer's limits. After conquering foundation challenges, crews faced erecting the 2 backbone columns, the main towers, one reaching 262 meters tall, the other 205 meters. These serve as anchoring points for the entire load-bearing cable system. They had to be constructed directly on mountainsides hundreds of meters above the gorge. Along with towers came the 2 massive cables, each weighing over 9,000 tons. These towers would support the bridge like giant pillars holding a ribbon in midair. Stability became critical, so the entire structure required reinforcement with high-strength steel capable of withstanding strong winds, vibrations, and earthquakes throughout its design lifespan. But those massive towers couldn't function without something even more critical, the cable anchor system. And that's where engineers faced a challenge that almost killed the project. The anchors function like giant counterweights, locking the 2 main cables firmly into mountains. On the Zhenfeng side, the gravity-type anchor sits solidly on the mountainside, with total concrete volume reaching 164,000 cubic meters, an extremely stable resistance block. But the Guanling side presented a nightmare scenario. Behind that tower stood a steep mountain with extremely limited flat land available. Placing a massive concrete block on the surface was impossible, so engineers made an audacious decision. carve deep into the mountainside, and attach the anchoring system directly to natural rock, transferring full cable tension into the mountain itself. Using the mountain as a natural anchor saved space while increasing stability, but excavating deep into unstable rock while maintaining structural integrity, that pushed construction technology to its absolute limits. One collapse during excavation could have buried workers alive and destroyed months of work. They proceeded anyway because there was no alternative. Then came the phase that terrified even experienced workers. After completing anchor blocks, crews needed to install the catwalk, a temporary walkway suspended between the two towers where workers would construct the entire cable system. To pull the first pilot line across the gorge thousands of feet deep, engineers deployed drones, making the wire guiding process safer and more precise than traditional methods. Once the pilot line was successfully pulled across, the catwalk formed, creating foundation for the most critical phase, constructing the bridge's two massive main cables. Workers would perform this work suspended in mid-air at extreme altitude with nothing below them but empty space and violent winds. What happened next would determine if the entire project succeeded or failed catastrophically. Each main cable consists of tens of thousands of high-strength steel wires twisted together with absolute precision, forming a structure capable of carrying tens of thousands of tons of load. On the catwalk suspended in mid-air, workers installed each cable strand. Every strand made up of 91 high-strength steel wires measuring 5.7 millimeters in diameter. These were pulled back and forth between anchor points under GPS supervision, maintaining error margins less than 2 millimeters. In conditions of high winds at elevations of thousands of feet, controlling every movement of each strand became critically important. One mistake and the entire cable system could fail under load, causing bridge collapse. Once all 217 strands were installed, a cable compacting machine compressed and bound them into circular cables using specialized compaction processes. Then cables were wrapped in multiple protective layers, resisting corrosion, weather, and vibration for decades. Only when these two massive main cables were completed could the bridge move to its next stage, suspending the bridge deck in mid-air. But that phase would prove even more dangerous than cable installation. Once main cables were completed, the bridge entered its decisive stage. First, engineers installed the system of vertical suspenders, each one attached to main cables using specialized clamps capable of withstanding thousands of tons of force. These suspenders transfer load from the bridge deck to main cables, then distribute it to the two anchorage points. Next came the entire bridge girder. 93 steel segments lifted one by one from the canyon center, gradually extending outward toward both sides. Each segment, weighing hundreds of tons, was hoisted using pulley systems suspended more than 2,000 feet above water and connected to suspenders through specialized load-bearing joints. During installation, engineers constantly adjusted cable sag, tension in suspenders, and position of each panel, ensuring the entire deck remained aligned without tilting or twisting under wind forces. Once all 93 segments were in place and connected into unified structure, the deck system was constructed on top, transforming suspended steel framework into fully functional expressway. But would it actually hold? There was only one way to find out, and the test would either validate everything or reveal catastrophic design flaws. In August 2025, the load test began. 96 heavy trucks with total weight of 3,700 tons were positioned across the bridge, evaluating load-bearing capacity and dynamic performance. More than 400 sensors recorded data on deformation, stress, and vibration, ensuring the bridge met the strictest safety standards. This wasn't just about confirming absolute safety, it demonstrated breakthroughs in real-time structural health monitoring. The bridge would continuously monitor its own condition, detecting problems before they became dangerous. The test succeeded, but construction had faced challenges nobody anticipated, challenges that pushed human endurance beyond reasonable limits. Throughout construction, crews constantly battled extremely harsh conditions from both nature and terrain. Huajiang Gorge is notorious for strong winds. During favorable seasons, wind speeds reached level 14 on the Beaufort scale. Construction halted whenever winds reached level 6 or above, ensuring worker safety. When transporting steel girders to installation positions, stabilizing ropes, sometimes tangled, forcing workers to manually straighten them, keeping lines balanced between upstream and downstream sides, minimizing twisting risk. They began working at 6 a.m., often not returning until after dark. Beyond wind and rugged landscape, the sheer volume of construction materials posed major challenges. The bridge required 439,000 cubic meters of concrete, equivalent to 176 Olympic-sized swimming pools. To reduce costs and protect environment, engineers reused waste rock produced during construction, crushing it into high-performance green mineral powder, using it as supplementary material, replacing 20% of cement in every cubic meter of concrete. This approach saved cement, reduced costs, and made full use of waste rock, helping limit pollution and conserve natural resources. But after all that effort, did it actually matter? Would anyone use this bridge, or had they built a monument to engineering hubris? In the past, traveling from the bridge area to Huajiang City took at least 3 hours. Now it takes no more than 1.5 hours, saving nearly half the time. Faster travel benefits not just local residents, but thousands across the region. As a combined transportation and tourism project, Huajiang Bridge was designed ensuring both structural integrity and visitor experience. With wide views, ideal elevation, and beautiful scenery, both sides were equipped with safety rails and specialized pavement coating, supporting high-altitude adventure sports. Inside the steel girder runs a visitor walkway that, if not built for tourism, would simply serve as maintenance passage. By connecting to the G56 expressway, the bridge shortens travel time while opening regional trade routes between China and Southeast Asia, attracting investment, creating jobs, and improving education, healthcare, and tourism. The bridge transformed an entire region from isolated backwater to integrated modern economy. But it represents something bigger than economics. China's Huajiang Bridge, standing 625 meters above the Beipan River, spanning 1,420 meters, requiring 93 steel segments, each weighing hundreds of tons, suspended by cables containing tens of thousands of high-strength steel wires twisted with 2mm precision. From drilling through unstable rock to workers installing cables suspended in clouds to load tests with 96 trucks, proving it could actually work. The world's highest bridge proves that altitude, terrain, and physics are just problems waiting for solutions determined enough to solve them. What amazed you most? The cable precision, the anchor engineering, the sheer audacity? Drop your thoughts below. Thanks for watching Macro Forge, where impossible is just another Tuesday. See you in the next one.